Hey everybody, I just realized that I recorded this entire week's content using the wrong monitor. So basically it was just a video of me sitting there talking to nothing, and there was a blank screen. So that was a lot of fun. I'm going to try not to do that again. So welcome to this week. This week we're going to be talking about the basics of learning. What do I mean by that? Specifically in this class, in this week, we're going to be talking mostly about the beginnings of associative learning. So we've already talked about this a little bit in the past, but we talked about how classical conditioning can be a form of learning. That's what this week and the next week and the week after that are all looking at. So specifically in this week we are going to be looking at creating these associations using sensitization and habituation. Next week, we're going to be talking a little bit more about some of these processes, but also classical conditioning. And then finally, in the week after that, we're going to be talking about neuroplasticity. So we will be talking about how our brains are changing as a function of learning something. So to get a big, broad picture, when we remember things, when we access information, when we encode information, all of that stuff changes our brain at a cellular level. Essentially, this week is going to start a 3-part event that is going to get us to answering why that happens and how it happens. So, before we get into too much about that, I want to quickly introduce this week's articles. So we have 2 articles. I'm going to quickly show them to you. So the first one of these is going to be the neurobiological... the first one is actually going to be this one, which is Edward Tolman's pivotal 1948 article, Cognitive Maps in Rats and Men. So this, if you're keeping time here, if you're playing along at home, you got your spirit board, you got your timeline, drawing out where all these articles are happening. You'll notice that this is the earliest article besides Ebbinghaus that we've talked about this semester. This happened before the cognitive revolution. When I teach history of psychology, when I teach that class, usually I talk about Edward Tolman as being one of the very, very first cognitive psychologists. Now, he didn't really consider himself that. He considered himself a behaviorist, and a lot of his measures are very, very behavioral. He was very much interested in in operant conditioning and things like that. But he had an animal lab, and he would test rats in different kinds of mazes and different kinds of puzzles, and he would observe how they learned these things. And what this particular article is him kind of coming to grips with there are some things that he has observed in his laboratory using these rats that are not easily explained using operant conditioning, using the principles of reinforcement and punishment, that seem to infer that there are some kind of invisible mechanisms, cognitive mechanisms, thought processes, mental events, however you want to frame it, that there are some of those things that happen that are influencing the behavior here. And so you may have actually learned about some of these before because they are very popular experiments, but they're really cool. I'm excited to talk about them. But the reason why we're talking about them here is because essentially what he sparks in this article is going to influence George Miller in his magical number 7 plus or minus 2 is going to influence everything. Because essentially what he is showing is that there are some things that are not easily accountable using operant conditioning, but that doesn't mean they're not important. The second article that we're going to be talking about, the modern article, is by Malad and colleagues. This one is a little bit more technical, of course, but it is super important. This article is all about how or people who have PTSD have tremendous amounts of trouble unlearning those paired associations. So, for example, and I'm going to try to give a broad example without too much details. Let's say that if I have PTSD and it is related to a house fire, for example, and the last thing that I was eating before the house fire was a couple of pickles. So now whenever I see pickles, or I smell pickles, or I taste pickles, I have these paired associations with something very traumatic in my life. And let's say that that was so traumatic that it gave me PTSD. Now, whenever I eat pickles, I have this anxiety reaction, I have this panic attack. The question then is, why is it that people who have PTSD seem to have tremendous difficulty being able to unlearn, quote unquote, that paired association? What this article is going to show is that there are certain parts of the brain that are different for people that have PTSD and people that do not have PTSD. Something about that traumatic event changes the circuitry of the way that these areas interact with one another. Alright, so it's very fascinating, very pivotal, very important article, and we'll talk about those soon. Alright, so basically what we're going to be talking about this week is classical conditioning. And some of these things I'm going to kind of skim over because we've kind of talked about them a little bit. But the first is kind of identifying what a memory is, and we've talked about this, that for the most part when we think about memory, we think about recalling lists of words, remembering phone numbers and things like that, remembering things for an exam maybe. But this semester we've talked about how there's much more to the picture than that, right? That you can include things like implicit memory, right? So procedural learning and learning how to do certain procedures, that those are all important things in memory. And so there are some things that we do that we don't normally think of as memory. But then the question that I'm interested in is, can you think of any kind of behavior that you can do that doesn't require some form of memory? In other words, that you don't need prior experience or any history to work. So while you think about that, I'm going to take a sip of coffee. Alright, so what do you think? Are there any behaviors that you can do that don't require some prior learning? Yeah, in the back. No, actually I can't. I'm not very good at improv, so I was going to try to to keep that up, pretending that there's somebody there. Anyways, yes, there are certain behaviors, but they're kind of tricky. One of the most kind of common popular versions of this are reflexes. That we have reflexes and we do not require any kind of previous behavior to do those behaviors. So you can think of it as the simplest expression of behavior. You don't need memory to have a reflex. This is because they are innate and they are involuntary. Those two words are important. Innate simply means that we don't need to learn them. They come with the hardware. They come with our bodies. That we have reflexes that we do. We don't need to learn them. They come pre-programmed. They come factory made, whatever. The second word, involuntary, means that you can't help it. That is something that doesn't matter what your feelings are about this thing. It doesn't matter. Doesn't matter if you want to or not. You do it. So they are involuntary and they are innate. You don't need any learning to do that, and that's because a lot of this stuff is going to happen at very primitive areas in the brain, sometimes in the very base of the brain, sometimes in the spine, that these are things that don't require higher order processing to be able to do. Some examples of reflexes you can find here. There's a really cool, cute video of a developmental psychologist demonstrating some reflexes on her newborn son. But, as an example, those of you that have been around children know that if you put something in their palm, that they will grasp it, right? That grasping reflex is involuntary. The baby doesn't mean to do it. It's an involuntary reflex. You could put anything in that baby's hand and it would clench it. You could put a penny in their hand and they would clench it. You could put a set of keys in their hand and they would clench it. It's because it is involuntary. So no prior history is needed there. Now, whenever we start talking about this, and the reason why this is important is because everything that we do comes out of these reflexes. So one example is that if you put something in your mouth, you will start to salivate. And I'm sure that you've heard enough about Pavlov and his dogs and things like that. But that's a really salient, clear example, right? Pavlov's dogs, they would drool whenever they heard the sound of a bell, the sound of a metronome, because they knew that food was on the way. So the reason why these reflexes are important is because reflexes are going to start um, these behaviors. So for a dog, for anything, if you put something in your mouth, whether it be food or not food, I could put this penny in my mouth and it would cause me to salivate. Why? Because that is the body's natural response to try to digest something. It's involuntary, it is innate. Babies don't need to learn to do that. We don't need to learn to do that. So that kind of involuntary response is then going to be paired with something that has happened. Maybe it's the pair of smelling something. Maybe it's the pair of seeing something. But that association is then going to be made. Now, before we go too much further, next week we're going to be talking about an article featuring this guy right here, this disgusting, slimy sea slug. This is called Aplysia, and it is a sea slug, and the reason why a lot of the research that we're going to be talking about, some this week, a lot next week, comes from the sea slug is because they are very simple organisms. What I mean by that is that they have relatively few neurons, and their neurons are actually pretty big. And because of that, they have become an ideal test animal, an ideal test subject for a lot of this research. So a lot of what we know about the fundamental pieces of memory come from the Aplysia. They come from the sea slug. So why is it important? I just talked about these things a little bit. They have relatively few neurons, 20,000. That sounds like a lot, but keep in mind that we have like 70 million. And so it's really easy for neuroscientists to try to see what's going on in the nervous system of a sea slug. Very easily identifiable and observable. And some of the muscles that these sea slugs have can be controlled by as few as a pair of neurons. You're not going to find that really in the human body anywhere. So it's really easy to do an experiment to see what happens whenever you manipulate this neuron, whenever you activate it, or whenever you inhibit it, to see what kind of influence it has on their behavior. So its behaviors are very clear and rudimentary. It's mostly just a lot of movement-based things, so it's very easy to observe. And it does, because it has a nervous system, it does learn from its environment. So a lot of what we know about how memory works is going to be based on learning from these studies back in the 70s up until today. They're still widely studied. All right, sorry, let me moving things around. I'm not going to go into this too much because I hope that you, if you're a senior, you already know the structure of a neuron, so you already know the basics of how these things work. If you don't, just look at Wikipedia. The important things to know here are going to be the dendrites and the axon endings, because as one of these cells is activated, it is going to go on to influence other cells. One of the things we're going to learn in 2 weeks from now when we talk about neuroplasticity is that depending on how these things interact with one another, depending on how they respond with one another, is going to influence how strongly these connections are being made. So when we talk about the Aplysia, the sea slug, and how it has these two connections, that's a super simplification. That is very easy to see how one cell is going to strengthen its response with another cell. It's another thing altogether to think about this with humans, where we have not just a couple of neurons, but several neurons that are all kind of connected in different ways. It makes things very, very tricky to directly observe. So that's why a lot of this stuff is going to deal with rats. It's going to deal with slugs, because they have more simplified nervous systems than we do. All right, so this is a good spot for me to pause it. I'm going to stop this video here, and then the next video we'll pick up and talk a little bit more about habituation and sensitization.